Good afternoon, ladies and gentlemen. You're all very welcome to today's webinar. My name is Martin O'Gara and I'm presenting this webinar today, and today's topic is the MasterFrame Dynamic Analysis and MasterFrame Seismic Analysis, where specifically we'll be looking at vibration design in the dynamic analysis module. Before we proceed, I just want to do a quick housekeeping check. If you can just raise your hands, please, on the little raise hand symbol, if you can all hear me. And yeah, I can see some of those hands going up there, so that's excellent. Okay, I'm just going to drop those hands and we'll just proceed then. So thank you very much for that. As I say, today we're going to be focusing on particularly vibration design before we take a final look at some seismic analysis. Now we'll actually be presenting two different MasterSeries modules here today, obviously with a related topic of dynamic analysis. The modules are separated in that we have our MasterFrame Dynamic Analysis module, which includes the modal analysis of establishing natural frequencies and mode shapes. And as part of that module, we have the vibration design checking to the various different codes that one would use for these types of things, SEI P354 primarily, and the Concrete Society CCIP 16. We're going to look at a particular couple of examples with regard to that today. Before moving on to our second module, which is MasterFrame Seismic Analysis, whereby particularly we'll spend a bit more time looking at a response spectrum analysis and how you can apply that to your model for design purposes, as well as comparing that to an equivalent lateral force method. But we'll talk more about that as we go. So particularly, we're going to start off looking at the vibration design. Now, it's fair to say that in recent years, vibration design is something that has a very much a raised profile. We have moved beyond the traditional design of simply looking at natural frequencies, say of composite beams, and ensuring that they're below a certain magic number. We understand now as engineers that there are actually more important or other more significant factors, and this is where the vibration design comes in. And primarily, the focus is on the something called a response factor, and establishing a response factor, which is simply a measurement of how comfortable a floor or a system might be to a user, which is all based on the actual accelerations that that structure would experience with a given set of excitation forces. So if you're unfamiliar with that type of analyses, I would highly recommend that you have a look at the SEI P354 or the Concrete Society CCIP 16. They are give you an excellent overview of the theories and the science and the application of that also. So we're just going to break from this presentation here and just go straight into the program, and we're going to take a look at a couple of examples whereby we'll firstly do a little bit of floor vibration design. The SEI P354 does actually state that in its title that it is design of floors for vibration. However, it isn't exclusively floors that the publication applies to. We'll see in a while how we can use it for helical stairs or any other type of structure essentially. But what I do have here in the first instance is a very simple composite floor plate. Opening up this model, now there's a range of fundamental key differences between this particular model that we've set up for the establishing the floor vibration design and what you would typically use for your standard static analysis. Your standard static analysis, you would essentially apply your loading as what we call gravity area loading through the model management tools. So that would typically be done if we go into the editing environment. Just giving that a second, and we've got 3D model, and we would apply our gravity area loading and the likes in this fashion in a static model for simple static design. However, for dynamic analysis, the actual stiffness of the composite floor plate and the continuity of the composite floor plate is of prime importance. In simple dynamic or simple traditional static analysis, we look at these beams individually and we apply composite design theory. all we need to know really is the thickness of the deck and the type of the deck, and we work out composite inertias as such, and we apply those types of theories. However, for dynamic analysis, the continuity of the deck is really important, and the actual accurate stiffness of the system is important. And to that end, we don't apply our area loading in the traditional static sense. The first fundamental key difference is that we have actually applied a finite element surface to this composite floor plate to represent the decking. So here's our finite element floor plate. There are separate webinars on MasterFrame Finite Element, which is another module add-on to standard MasterFrame. If you would like to find out a little bit more about that, you'll find the links to the recordings of previous webinars. But essentially we've got a surface, a single surface set up here. And in this surface we define things like its openings, just as you would do for a normal flat slab, for instance. However, one of the key things here is that we're actually modeling a ribbed slab. Now we do have a little drop list here of the MasterSeries inbuilt library of metal deck profiles, and you can select one of those and apply those deck dimensions, which essentially just sets up the basic dimensions of the decking for analysis purposes. Another important feature is the orientation of the ribs to the axes of this finite element surface. Back here we can see the x-axis, the local surface x-axis of the surface goes like this, but obviously we would like our ribs to go perpendicular to that, which is why we've got a rib axis of 90 degrees specified here. Typically also for concrete, for standard structural analysis for static design, you might expect to see a Young's modulus value of in around 24. However, interestingly, and actually for all things modeling orientated, I would recommend that you look at section 6.1.1 of the SCI P354, which discusses a range of modeling issues, such as the value of the Young's modulus to use, and so that experiences an increased value for this dynamic state that we're looking at. Of 38. Now, conversely, as to go along with that, the shear modulus is also increased, which is also has a relationship with Poisson's ratio. So a few things there that are different from your normal static analysis. Another quite important point is the fact that all the structural beams that we see here are specified as attached beams in this finite element surface, and also key to the correct modeling of this scenario was also that the fact that these beams are specified as being bottom justified to this. So when we actually turn on the 3D profile and zoom in a little bit, we can see that if I just move away from here, that we've got our decking and the beams are indeed bottom justified. That obviously gives you the correct offset that you require for the correct calculation of the composite inertias. Okay, so that's the finite element surface setup. Another key thing that section 6.1.1 of the SCI publication talks about is the fact that we don't need to consider applying end releases. So when I turn on my end release symbol, we don't see anything here, and that's really because it states that at the levels of deflection that we're looking at and movement that we're looking at during a vibration, that the joints would still be have reasonable rotational stiffness for what we're looking at. So that it recommends that you simply don't apply those rotation or those end releases in that scenario, combined with the fact that the deck is continuous. So that would obviously mitigate the full end release that you would otherwise might experience anyway. One other point that engineers maybe often don't think about, and again is covered in the SCI publication, is the loading on the structure and what aspects of those loads contribute towards the natural frequencies of the structure. And typically, obviously, any permanent mass loading, as permanent loading or dead loading, as it would refer to in the 5950 terminology or BS terminology. So that loading obviously would be fully included in the mass, but also there's recommendation that one would consider including up to 10% of the live load in the mass contribution. Now the loading here is defined just as you would do on any finite element surface. In fact, if I just pop back into the finite element surfaces, we can see here that the loading is applied directly to here. Oh, in fact, I don't have any load, it would seem, other than what I get from just my standard self-weight of dead loading. But if I wanted to, I could apply another new load and make that a full surface area load, say for example a live load, and then I would have some component of live load to take into account, whereby I could apply a factor to that at a later stage of, say, the 10% that we've talked about. So I'm ready now to go into the dynamic analysis, so we'll just exit from here into dynamic on the top menu bar. Okay, during this time it is actually recalculating a lot of the mass and stiffness matrices as we proceed into dynamic, and for this type of structure it can take a little longer. So here we have a previously analyzed set of results, and essentially what we gain from that is a series of natural frequencies and mode shapes. Now a few things to consider and how you would achieve that is, first of all, is of significant importance is that you consider what mass you're including in your structure. Now I can see here, whether right or wrong, that this structure has a 1.25 factor on the dead load. I'd probably disagree with that. I'm not going to change it now because it would warrant a reanalysis, but it's probably more accurate to say that simply that you've got simply a unity factor on your dead load. And if you do want to consider, say, 10% of the live load, you would have a 0.1 factor in here. The self-weight of the slab that we included in the finite element surface is automatically included here, as is the self-weight of the members, providing we've checked this box and we've also put the factor against the D1 load group as we have here. So that's absolutely fine there. For small structures or non-finite element structures, it is often absolutely fine to say that you want to calculate practically all natural frequencies in the range of 0 to 1000 Hertz. Now when you are using finite element analysis, would highly recommend that you don't calculate all the natural frequencies, because that has an adverse effect on the analysis time, but also an adverse effect on the amount of memory that's required. So it would typically not be necessary to calculate all natural frequencies in a structure. But the question is, how many do you calculate? And that really, the question is very much related on what you're after, what you want to establish natural frequencies and mode shapes for. In my case here, I want to do a vibration design check. And I know in my vibration design check that I'm going to be looking at walking frequencies in a range of 1.8 Hertz to 2.2 Hertz. And with the various harmonics, the fourth harmonic might make natural frequencies of up to 8.8 Hertz important to me. We'll discuss a little bit more about that as we continue. But we can see that anything in the region of 8.8 Hertz and above, or up to 8.8 Hertz, would be important. Now I've calculated 100 frequencies, which is my initial guess at how many frequencies I may require. And looking at the number of frequencies that I've come up with, it's got 100 frequencies, but the highest frequency is 27 Hertz. So the highest frequency is well above the range of important natural frequencies. So when you get to that order of frequency for a walking vibration, it would have little or no impact on the contributing to the response factor. So I'm happy that I've only got 100 frequencies here, and they stop at this particular natural frequency. And indeed, we can see when we look at the mode shape, just increasing the scale a little bit there, sorry, that's the speed, that it is indeed quite a high order of which would have pretty low mass contribution as well. One of the things to keep your eye on is the overall mass participation. Typically the codes recommend that you would be seeking a mass participation of 90% or above, which we are actually getting in the lateral directions, but for the Y direction that's not so. But as I just stated, I'm happy that my maximum value of frequency is well outside the range of frequencies that I need to. So I know that all frequencies below 27 Hertz have been considered. In order to view what perhaps are the important mode shapes, if you wanted just to examine those, you'll find these mass participation columns very, very useful. You can sort by mass participation in the various directions. So for instance, if I were just to sort by frequency, which is the default, I can see here that the lowest frequency is 1 Hertz, and you might look at that as a number on its own and say, that's bad, we don't want composite floors with a frequency that low, but that's actually a lateral mode shape, which doesn't have any influence on the vertical mode shape of the structure whatsoever. And the mass participation essentially clarifies that to us to say that it's got zero participation in the y direction. So if we filter to or sort by mass participation in the y direction, we start to get to the mode shapes which are indeed important to us. So that mass participation filter or sorting technique is quite useful. So we're ready now to move on to the vibration design. Now I have a vibration design case already set up here. Perhaps what you might see when you come in, if I were just to perhaps reset this, let's just delete that. You might come in with no vibration design cases. We can have multiple vibration design cases, and you'll see perhaps the need for that as we continue here. So first step, add a vibration design case, and we choose our code. I'm going to say that it's a residential non-critical area, maybe with a damping ratio of 3%. This is the codified value of the weight of a single person, which is something you generally don't change. I'm going to say for now that I'm wanting to look at a steady state. I'll talk a little bit more about when to use steady state and when to use transient in a moment or two. And I am interested in a walking frequency type of situation. There are other types of Fourier series of types of excitation force, aerobics, high impact, things like that. You even actually can have your own user-defined Fourier series, which isn't very often used. But we're interested in simply just the walking frequency, and these are the recommended ranges of frequencies of walking that particularly the SCI P354 determines. So we're examining the different responses of the structure between different frequencies of walking of 1.8 to 2.2, and we look at all other frequencies in between that and up to 100 steps. That 100 steps can have an impact on the amount of time this vibration design analysis takes. If you wanted to reduce that somewhat in the initial instance, you could take that down to a value of say 10 steps or 20 steps for instance, and that would be a benefit to the analysis time, or the time that the vibration design takes when we actually click on this button to perform the assessment of the vibration design. So we have here the standard Fourier coefficients that are determined in the SCI P354 for a walking frequency, if we want to have a look at those. Now coming along to this area, this is really important in that in understanding what we're actually trying to measure here. What we're trying to establish is something called a response factor, which is a measure of how comfortable the structure is at a particular point to a user or to an occupant or a person who's occupying that space. So the response factor is due to the response at a point is due to excitation or load being applied at a point, which could be anywhere in the structure. So in theory it's possible to measure the response at say a node here due to excitation force being applied at a node here. So when you think about it like that, there are if there are 1,000 nodes here, there are n to the 1,000 combinations of different response factors of the response factor at this node due to the loading being applied at this node, and so on and so forth. There are a lot of combinations. In the initial instance, it's probably fair to assume that the worst response factor at a point occurs due to loading being applied or excitation force being applied at that same point, which is what this checkbox is all about. We're going to say here that the response node equals the dynamically loaded node. We also have the option to look and investigate the response factor at just a single point or a range of points. So I'm just going to do this for the whole floor plate here now, whereby I'm going to select all the nodes. Now you notice here the response nodes aren't highlighted, just the loaded nodes, and that's because we're saying, well, we're measuring the response at the same node that we're applying the load at, so that we don't have this array of combinations to consider. So let's select those, put that on a side elevation there, and we'll just window all those nodes in that floor plate, and we have all those selected. So let's action now our first vibration design case. Oh, another little point to note is that we are interested in the response factor due to someone standing on the floor, not lying down in any one of these directions, but standing on the floor. So their torso is vertically aligned to our y-axis. And we've established here with this nice color-coded regions that we have a hotspot of response factor occurring around this location here. And we have the values of the RMS acceleration, and that quickly or very conveniently gets converted into a response factor at that location. Now we can see here that the response factor is 26. It occurs at a frequency of 2.06 and at this particular node. So it's examined all these range of frequencies in 20 steps, and it's found out that the worst response factor at that point occurs at this frequency, whereas you can see other nodes, the worst response factor occurs at the upper end of the frequency range, with the odd one occurring at other frequencies in between. So we can look at this value of response factor, and if we want to then consider in more detail, well, what does the response factor actually look like for this point over this frequency range? I can actually add now a second loading case, and noting that the node is 684. And this time we're going to just say, well, I'm just interested in a single node, and I can pick it or I can just type it in there, 684. And if I do my vibration design now, we can see now we're getting the actual single graph of the relationship of the response factor. Sorry, that's the RMS acceleration. So you can choose the headings of these columns to move between. So we can see that you're getting the what I've noticed here is that I've added a second case, but I didn't change the damping for my second case. So if you're comparing cases, do ensure that all your variables are the same between each case as well. So we'll just run that again, and we can see that we're getting the 26.36 at this frequency. This time we're going actually over 100 steps, which I don't mind so much because we are simply looking at one node and not the hundreds of nodes that we have in this floor plate. So that's my way perhaps of examining what happens at, say, a critical node. So the first case maybe highlights me or zones me in on where is important, and then this is telling me actually what is the behavior at that node over the walking frequency range. Sometimes you get various different peaks here as they interact with the different harmonics, all depending on your actual frequency values that are relevant to that part of the structure. Actually, it is also interesting sometimes to note which mode shapes are important to this. Now, this is something we've worked on for the 2015 version. It has been noted that whilst we have a response factor here of 26.36, it is actually, and as the code states, it is summing up the response factors through a square root sum of the squares type of combination of all the different mode shapes. Now, engineers are saying to us, well, actually we'd like to know which mode shapes are important, or which frequencies are important along with their mode shapes that contribute to this value, so that perhaps they can go and look at those particular mode shapes and see what can be done to tune them or to reduce them. Now, looking at the mode shape, I would have suspected that mode shape 4 here would have been a fairly prominent mode shape that would be important to this response factor. Instead of using all mode shapes, I could say, well, I just want to use mode shape 4 on its own, and let's run that again. And we can see, yeah, we're getting a response factor which isn't quite 26 but 23.8. So that mode shape 4 shows us that it is the most contributing mode shape to the overall totaling up of the response factor from all the different mode shapes at this particular node. So that's one way perhaps at the moment of identifying which mode shapes are the important ones, and the engineer might do something to alleviate that or to get around that. Now, I'm going to move on to a third design case. In fact, I'll just actually reuse my first design case and talk about the final scenario of whereby your response nodes are not equal to your dynamically loaded nodes. And this does introduce a significant overhead in terms of what we're considering. If we take, for instance, the example of where this might be a critical area, such as an operating theatre, and we may have a corridor running outside that operating theatre, and I'd like to know what the response factors are in that operating theatre due to someone walking down the corridor. And this is where this is a case where the response node not equal to the dynamically loaded node might be important or relevant to us. So let's go and select some nodes, and this time we're not selecting the whole structure. We're going to clear that and just put that on a plan. And I'm just going to select the nodes in this region for the, sorry, that's the loaded region. That's not what we want. Just come into that again and clear that. And say, for example, this is our loaded region. And this is our response area. So we're loading the corridor and we're measuring the response in the operating theatre. So let's run that. And this time it has to look at every single one of these nodes and their combination with every single one of these nodes. So you've got quite a considerable extra amount of operations going on there to establish what are the critical and key response factors in all of this. So it is taking a little bit more time. Okay, so now I've got my response factors in this area because this is where I've said I was measuring things at. And my critical response factor is 8 Hertz, or sorry, 8 simply as a response factor, occurring at the walking frequency of 2.2 and being measured at node 1037, which is the red node, and the blue node is the node at which the vibration, the excitation force was applied. So we've got a critical situation here whereby when someone is walking at this point, you get a maximum response factor occurring at this point. That type of information certainly can be very, very useful to you. So that's just a little bit of a summary on some of those individual options there. Now, I want to move on to perhaps considering, I said I'd talk about situations whereby the steady state may not be applicable and we might need to use the transient. Just to explain, I suppose, what we're looking at here in this type of floor vibration analysis is something called a steady state type of loading, whereby the walking activity is considered to be applied in a continuous sinusoidal type fashion as shown here, without any intermittency or anything like that. So in fact what you get through this response factor is very much a critical scenario, or the worst case scenario. Now there are instances whereby the steady state may not be the worst case scenario, and that's whereby in cases where the frequency of application, which is determined by the various different codes, this is the range which is determined by P354 for walking, if the primary response factor, or primary, sorry, let's get the terminology right here, if the primary mode shape or frequency of the floor, let's go for some of our different mode shapes. So say for example this mode shape, if the primary mode shape of the floor is much higher than the frequency of the load being applied, then you may be into a situation where the steady state isn't the most critical, but what's something called the transient state is more critical. Now there's a very, very good image of this here in the SEI P354 in section 2.4.3, if you want to take a note of that, and it demonstrates to you what can happen in situations where you've got a very stiff floor with a high natural frequency in that you don't actually end up getting into this steady state situation. You end up getting what's called an impulse type of vibration as a heel might strike a floor, and you would get a series of these impulses. Now that doesn't lead itself to a steady state situation, but what's called a transient situation. You get a higher peak acceleration at the heel strike, which then dissipates out to a much lower steady state. So therefore the transient situation actually causes higher peak accelerations and therefore larger response factors. In the transient situation, what you're doing is saying, well, this is the total time that this condition is going to occur over, or this is the period of time over which I'm going to measure this transient situation. And again, there's recommendation given in P354 with regard to what sort of time period that should be. The time step is really just the increment in which, because the standard transient state is a simplified assessment whereby it says everything operates in a sinusoidal fashion, so therefore we don't actually need to iterate every single step in time. We know what the peak acceleration is going to be because it's a sinusoidal type of behavior. But in the transient state we actually have to do a full analyses or time history analyses at a series of times and sum them up, sum their accelerations up to give us an RMS acceleration, which we then can convert. So the time step then is quite important, and obviously the lower the time step, the more accurate that's going to be, but it is going to take a longer period of time as well. So that's something just to bear in mind. In section 2.4.3 of the 354, SEI P354, it does give you an example of floors with a frequency above 10 Hertz, where your highest fundamental walking frequency is 2.5 Hertz would be a case whereby you would consider transient design instead of steady state. We ourselves don't give you any warnings or anything like that as to when you might be using transient or steady state. That is in a decision which should be is entirely in the hands of the engineer, just to make that absolutely clear. Okay, I'm going to move away from this example now and open up another example of a staircase, which will allow me to talk about a few other aspects of vibration design. Okay, let's go for our helical stair. I have a little staircase here, which is reasonably interesting and complex. Okay. Now the analysis has already been done here. Something like this would analyze in a matter of seconds anyway. I have actually analyzed all the frequencies. You can see my mass participations are above the 90%. So I don't need to worry actually in this situation about looking at the frequencies to ensure that I've included enough of them, because actually the frequencies get pretty big pretty quickly anyway. So that's not a major concern of mine. In fact, it's more than likely the case that simply just this one mode shape will be the dominant mode shape that'll control all of my response factors for anywhere in the structure. Okay, now I've looked at that and straight into vibration design. So I have a vibration design case here whereby I'm simply selecting all the nodes, and I'm using this assumption again that the response node equals the dynamically loaded node. That's fine. Key differences here on what I'd done previously was that I've actually selected that it's a staircase, which is important because it is a staircase. Another important point to note is as I would move between walking and staircase, you notice actually that this frequency range doesn't change, and that's because we leave that frequency range that you want to consider up to you. The codes, the SEA P354 gives recommended walking frequency ranges and staircase frequency ranges. However, sometimes they can be stipulated, so we don't set those in stone, so it's up to you to set the range. So when you go for a staircase, you might find that you need to modify that range to the recommended values of 1.2 to 4.5. So just to keep an eye on that one. Now if I do an analysis here, and we've got our response factors, and we've got a response factor here of 50 occurring at this node here, right up at the upper end of the frequency range of 4.5. Now this is where I want to talk a little bit about, one actually very useful feature here is if we turn on the 3D while looking at response factors, we saw the color-coded ranging that you got for the finite element, shell elements, but when you turn on the 3D button, when you've considered response factors for a multiple range of nodes, it will actually color code them, giving you a little red hotspot here to allow you to zone in on the parts of the structure that are, but this is actually ordered always on the highest to lowest anyway, and when you select that you usually get the red dot appearing as well, so it's not generally not that hard to identify where you are in the structure and what is important. Now I want to come on to talk about another aspect of vibration design whereby we're perhaps not dealing with a situation where our loading which we have applied would be of a steady state or a continuous type of nature. As I had already mentioned, the steady state application of loading really is your worst case scenario for continuous vibration. It's really assuming that this is a response factor that will occur due to this load being continually applied without interruption. Whereas in reality we know that structures aren't like that. People walk up and down corridors intermittently and things like that. Up and down this staircase, it might be some kind of staircase which is used very, very infrequently. And to take account of that and to modify that, the P354 gives us the choice to use something called vibration dose values. So the vibration dose value takes simply two parameters, and there's a simple equation for that in the P354. You can look it up, but it asks us for two items: TA, which is the duration that the loading takes place in. So you might estimate that somebody could walk down the stairs in 30 seconds. So that's the duration of the loading. The NA is the number of times this excitation may occur over a design period. Now typically the code splits it up into days and nights. It talks about an 8-hour night and a 16-hour day. So I might say, well, actually there's possibility at a maximum that this stair would be used 10 times over a 16-hour day. Now if I just rerun that analysis again, I can see along with response factors I also get vibration dose values. The vibration dose value is simply a different measurement of this response factor, and it's not to be correlated to the response factor as such. Response factors and what's acceptable in terms of a response factor again is talked about in these various different publications. I know that the 354 indicates that a response factor for a stair might be, I'm just going to quickly actually look that up in the acceptability criteria that it talks about, and we've got table 3.5 in the SCI P354, which talks about stairs for light use, for example offices, that you might be looking for a response factor of 32 or below. Remember, these values, the higher they get, the worse they get. Not like natural frequency values, whereby we're looking generally for higher frequencies, but no, we're actually looking for lower response factors. We're always looking for these values to be below a certain limit. The vibration dose value has a different acceptability criteria. Table 5.4 in P354 gives acceptable ranges of the vibration dose value. So for example, it's saying here, it doesn't actually have one for stairs, but it's saying for buildings for a 16-hour day, you're looking for a range of 0.2 to 0.4 for no adverse comment. For something called adverse comment possible as a category, it says 0.4 to 0.8. So if your client is happy to accept the possibility of adverse comment due to someone using the stair, depending on its frequency of use, you may be able to convince someone that this vibration dosant value is acceptable for the particular use of this structure. So that's something that might be interesting to some of you. The resonance buildup factor is another little trick that we can use to further reduce both the response factors and the vibration dose values, and it simply is an extra little reduction factor which can apply to these values to take account of the fact that the period or the length of the time that this loading activity occurs is actually quite short, and it really asks you for two things. It asks you for the path length, and then we actually give you the option to automatically work out the walking velocity from equation 16, which we recommend. And quite simply, when we look at how steady state sinusoidal response builds up, it obviously doesn't start straight into the steady state condition. It actually has a period where the steady state continuous vibration builds up. So this is what the resonance buildup factor is all about. It's saying, well, the actual loading activity doesn't occur for long enough to enable a full steady state condition to be reached. So this can actually have a beneficial effect in that it will reduce that somewhat. So I would estimate that this is about 10 meters long. It generally has quite a minimal impact, and you can see those values changed ever so slightly, but you might find that useful in some instances. Okay, now this really leaves me to focus on the last 15 minutes or 10 minutes or so on the seismic analysis aspect. So I'm actually moving across to a separate module here, which still is inside the same interface as such, but it's a separate purchasable module from the MasterSeries. So got a nice little simple structure here where I want to consider some seismic analysis on. So let's pop into dynamic. When it comes to seismic analysis, there are basically two different types of seismic analysis that we have on offer. And those of you who know what we're talking about, those are essentially something called the lateral force method, which is actually nothing to do with this area whatsoever, but and we'll see this a little bit later on, it's a simple method of applying equivalent static loads to a structure to simulate the effects of seismic analysis. And those lateral forces are determined using quite a simple technique based on the actual mass that's in the structure and how those lateral loads are then added and distributed throughout the height. We have a method in the MasterSeries which does that automatically. That's one method. The method I'm looking at here now is something called response spectrum analysis, which is a more sophisticated method of dealing with the seismic analysis of your structures. The codes of practice, whichever you're using, whether it's the UBCs or Eurocode 8, all give you quite strict guidelines on when you can use one method, either simplified lateral force method, or when you actually need to go to the response spectrum analysis method, are all dictated in the codes. So it's useful to know what am I allowed to use and what is beneficial for me to use. You get both of those methods as part of your MasterFrame Seismic Analysis license. As always, we've got to have natural frequency analysis done first of all. Again, for the simple structure, we've just calculated all the natural frequencies, even though many of them will be totally irrelevant. Let's just have a look at some of them. Just increase the scale. So we can see, perhaps if I see some vibration in the Z direction, some vibration in the X direction, so about 5 Hertz or so in the X direction and about 4.5 Hertz in the Z direction. So back over to the response spectrum tab. Now I have a response spectrum load case here, which I simply just added by clicking create new response spectrum case. And quite simply, the first thing to do is to select your code. So these are the different codes that we cover. Eurocode 8, IBC and UBC are the ones that we do there. One of the first things to think about is my structure aligned to the global X and Z axes? And in this case it is. However, this structure may have been rotated through, say, 45 degrees, for instance, in which case it's a good idea to rotate your result axes. These are the axes, the U and the V axes are the axes in which the seismic response forces are going to be evaluated in. And in fact, it's even more than that. It's actually reasonably critical that we would align the U and the V axes with the structure axes. But in this case, I'm happy to stay with 0. Generally these days, people prefer the complete quadratic combination method. I suppose really just to give you a little bit of background what's going on here, this combination is the way in which the various forces from all the different relevant mode shapes are combined together. Because just like, I suppose, vibration analysis, whereby you get a square root sum of the squares of the acceleration that occurs due to the various different mode shapes, seismic response is quite similar in that we're going to combine forces for lots of different mode shapes, and the way in which we combine those forces is determined here. And the complete quadratic method is a more sophisticated method which is recommended these days. So some basic settings here that are determined by the code to do with ground type and importance. You move to a different code, those values do change according to that code of practice. So these are specific to the code that you've set here. I would always choose design spectrum. I would have said damping, I'm going to drop that down to 3%, and this is my soil acceleration value, which is fine. And we actually draw the little response spectrum graph here, whereby this response spectrum basically gives us the peak acceleration which occurs at these various different periods, which is essentially another way of representing a natural frequency. So we're essentially looking at accelerations and combining them and converting them into forces is what's going on here. The Eurocode 8 and the various other codes asks you to determine sets of forces in two principal directions. So we're going to be considering sets of forces in the U direction and sets of forces in the V direction, which in this case are the same as the X and the Z. So when we click on that button to do the response spectrum analysis, it creates these sets of forces here. Now quite usefully, it's good to look at these guys down here, whereby, well, I think actually that's still in process. There we go. So these are my forces from the response spectrum of our set of forces that go in the V direction, which is this direction, and the set of forces which go in the U direction. Now you can see here actually what the total X and Z direction forces. Yeah, so the U direction, which is essentially the X direction, you can see here that it's got 72 kilonewtons in the X direction and 2 kilonewtons in the Z direction. Whereas the V axis has got a little bit more of a split, but primarily, yes, it's most of its forces being applied in the Z axis. So the question is now, what do we do with those forces? Well, we can take those forces straight into MasterFrame and apply them to a static load combination, and then treat that dynamic design simply as we would do any other, and we can establish all the bending moment diagrams in combination with any other static loads, any other static dead or live loads, as the code dictates, as the Eurocode 8 dictates how you would combine these forces with other forces. So let's get out of here. So we'll just exit MasterFrame Dynamic, saving what we've done, and let's go into the editing environment of MasterFrame. Okay, so let's go to loads, and I'm just going to straight to special loads or seismic loads here in this instance. So I'm back in normal MasterFrame now, out of dynamic, but still held in the dynamic results file are these sets of forces that I want to apply. So I'm going to say here, actually, I'm just going to go across and add a new load combination. So let's go to load cases and add a new case. And I'm going to call this load case dead plus, no, don't have the word seismic here. Let's go for yes. Okay. And let's get back to special loads, seismic loads. So for my second load case, I'm going to say, yeah, I've got my seismic loads. They are loads from a dynamic response spectrum analysis. So this is the dynamic response spectrum analysis that I've carried out. I only had one case of a response spectrum. You can have multiple cases. So this is my one case. And I'm going to say in this particular instance, I'm going to apply these loads with a factor of 1 for the U direction loads and a factor of 0.3 for the V direction loads, which is the sort of thing that Eurocode 8 would specify or asks you to do. So actually, while I'm here, I am also going to create another load case. Well, on load case 2, actually, I want to include my dead loads in this case as well. So this is my normal static D1 dead loads combined with my seismic loads that I applied over here. But I also want to create a second load case, or a third load case, sorry. We're just going to call this dead plus lateral seismic. So this is an alternative case whereby I'm going to apply my dynamic analysis or my seismic analysis through the lateral force method. So let's get it back across to special cases. So for this method, I'm saying, yes, I've got seismic loading, but I'm using the lateral force method this time. And again, go for factors of 0.1 and 0.3 in this instance. Now there are rules in the code with when you can apply this, and there's a couple of things you can actually pick out from here, in that all the relevant rules are equations and components in the code of practice that to do with lateral force method are specified here. So it's a moment resisting frame which determines the CT value. But there are rules with regard to the fundamental period, what's called T1 in the code, has to be less than 2 and also less than 4 times TC. So I've satisfied both those criteria. So if you know those criteria, you can pick up useful information here to establish whether or not the lateral force method is applicable. That is one of the criteria, but there's also criteria with regard to the regularity of the structure in EC8 for the lateral force method, so be sure to address all of those. And actually, what I didn't do to make this case compatible with the other one is also in case 3, I'd like to put in again 1.0 times my dead one load. So let's do a quick analysis. So we can see we've got seismic analysis on both of these. And into the output, so I've got my first load case, which is dead load on its own. So let's just look at deflected shape with a little bit of a magnification, not too much of a magnification. And if I move on to my second load case, dead plus seismic, I can see the nature of deflection that's occurring due to the seismic forces that are being applied. And I can view my bending moment diagram here for those seismic forces combined with my unfactored dead loads, remember, as well. And similarly, I have my dead plus lateral seismic, which is the simplified method of looking at seismic analysis, and you can see quite a similar deflected shape here. In fact, I can flick across to the tabular output, whereby I can get a quick look at the support reactions, whereby I can see that for my dead plus seismic, I've got 77 and 16 for my horizontal reaction values, but for my dead plus lateral seismic, 54 and 16. So actually a lesser value of load being applied through the lateral force method than it was through the dynamic response analyses. But it's comforting to see that we're in a similar sort of ballpark for those two figures there. So those are just some of the items on offer there in the MasterFrame Seismic Analysis. So really, guys, just to finish up, but yeah, guys, just to say thank you very much for your time here today. Those are just a summary of some of the items that we have looked at, and summary of the features of the two separate modules. If you're interested in a free trial of any of these components, feel free to inquire with regard to that. We can provide you with links to download a 30-day free trial on any of these particular modules. So we look forward to seeing you at the next webinar.